Speaker is Daniele Dorigoni, Ecalle's theory of resurgence, and I'll let you start right away.
Right. All right, so let me start as Goshali with a little recap of the last thing we saw yesterday. So we started understanding a bit better about the analytic properties of all these various direction of the summations. And in particular, we wanted to understand a little bit better how to capture the connections when we were integrating on the two sides of a Stokes direction, a singular direction in the Borel plane. And we could integrate on both sides, and this Stokes automorphism was telling us how to connect the resummation on the two sides. And just in the same way as the shift operator allows you to connect with translation, and the shift operator is the exponential of the derivative, we wrote the Stokes automorphism as the exponential of some new type of derivative, which is called the alien derivative. And just to give you the simplest example, if you give me a function which is in the whole complex plane just given by a pole plus a log, then the alien derivative is just taking the residue of the pole, multiplying by this unity delta, plus the minor, whatever is multiplying the log. So what we want to do today, we want to try and understand, well, we have seen that whenever we are generating this exponential suppressed correction, we might want to extend our algebra from formal power series to formal power series with these exponential suppressions. And as you have seen today in Gaussian-Stokes, this is in many cases not enough. You also want to add log of h bar. However, I'm not going to be discussing about the logs. And to see how this whole machinery help us, let me go through some concrete example. So for concreteness, let us take recut the equation once more. And let me write it this way, minus a phi plus z minus 2 phi squared equal to minus 1 over z. So this is where all the interesting bits are. We have seen already before that if we don't have the nonlinear term, sure, there are some asymptotic series behind, but the story is a linear problem. So we know pretty well what's happening to the Stokes phenomenon. We have seen many examples of incomplete gamma functions from steepest descent contour and so on. The nonlinearity, however, introduces some complications, but also some more interesting stuff. No, that's not for me. I just saw a message popping up in the Q&A. Good. So we can still find a perturbative solution. We can find a ARAW01 perturbative solution of the following form. So we have some factorial growth alternating in sign. From this term, given what we have seen last time, we would say, oh, that's great. There's just going to be a pole at minus a. However, because of the nonlinear term, the coefficients get polluted a little bit. They get polluted by some new coefficient Cn, which depends explicitly on a. And actually, a nice exercise for the students, although we're not going to have tutorials any longer, is to try and play with the various methods that, for example, Gerard has mentioned, and try to see what the singularities in the Borel plane are. And you will see that phi hat, the Borel transform, has simple singularities, not only at minus a, but actually minus a, minus 2a, minus 3a, and so on. So you might want to consider as a Riemann surface for this problem the universal covering of C minus this set. And we are led to consider, following what we were saying the other day, the algebra of simple resurgent functions, which is contained in, okay, as always, there is this constant part, it doesn't really matter, plus the simple resurgent functions, well, Resurgent functions on this Riemann surface. And the Stokes automorphism suggests that you might want to extend this object a little bit. That you might want to consider an extension considering e to the az times some new simple resurgent function, e to the 2az times a new simple resurgent function, and so on. So it tells us that we might wish to consider a trans-series ansatz solution to this problem, not just the perturbative one. So we can consider what is called a one-parameter family of the following form. Sigma is what I'm going to be calling the trans-series parameter. For a generic problem, you're not just going to have a single trans-series parameter, but this problem is simple enough that we can just get away with one. And basically, it's just telling you the grading of the instanton sectors. So we're going to write it as sigma to the n, the instanton action, the instanton suppression contribution to the n, and the instanton perturbative expansion phi tilde n. And we might want to try and solve this problem in this way. So this auxiliary parameter in here, but at the moment it's auxiliary, is actually going to play a key role. But if you wish, at this stage, it's just some sort of instanton counting parameter. So if you plug it in the perturbative, sorry, if you plug it in the Riccati equation, let me give it a name actually. Plug this ansatz in star, and we solve it order by order in the trans-series parameter, or equivalently order by order in the instanton suppression. So at the leading order, as we've seen already many times, there is actually nothing really, well, we already done the hard work. At leading order, we have solved the perturbative problem. Ordinary perturbative solution. What we called before, phi 0 tilde of z. This expression in here, which I didn't tell you really, but is a good exercise for the students to plug it in and play and find this coefficient solving some recursion. So no surprise, if you didn't put any instanton, the problem on its own, the perturbative expansion, doesn't tell you that they are there. However, we have already seen that from the Stokes automorphism, it suggests that we might want to look at something more general, and hence the trans-series ansatz. And at this point, the first non-trivial thing to solve is the order sigma to the 1, which fixes for us the one instanton sector in terms of the perturbative expansion. And you can solve this perturbatively. Solve perturbatively. And you're going to find a new perturbative expansion for this guy. And now you get the story. We go to higher order, sigma squared. We get the equation for phi 2, which is now going to be fixed in terms of phi 0 and phi 1. And again, you want to solve it perturbatively and so on. So in this way, we will discover that this perturbative solution belongs to C plus this algebra of simple resurgent function, where the Riemann surface is the universal covering of C minus A times Z. So we get all the singularities on this lattice, both at positive integers and at negative integers. Okay. So at this point, from these trans-series, we have that there are two singular directions. In this particular case, again, in general, you might expect a lot of singular direction. But in this case, we might expect that the Stokes automorphism in the 0 and the pi direction acts non-trivially, precisely because of the location of the singularities. Or alternatively, the action of the alien derivative will be non-zero on this point, possibly non-zero on this point. So this stage, I want to introduce this bridge equation, which is a way that is going to allow us to interpolate, or if you wish, to relate this equation in here to the Stokes automorphism, or equivalently to the alien derivative. And as the name suggests, this bridge equation is drawing a bridge between this alien calculus, the study of singular behaviors of the Borel transform, and standard calculus. In particular, this differential equation that we started with. So the starting point is something that we already mentioned yesterday. If you remember, with this new definition of the dotted alien derivative, we had that the alien derivative was commuting with the standard differentiation. So at this point, delta dot of omega phi will solve a linear and homogeneous problem. Let me do it for the example of the Riccati that we just studied. So let me act with Ka, with K an integer, on the whole Riccati equation, which I'm going to be rewriting. I don't know why, because you have it in your notes, but okay. This must vanish. However, we can easily rewrite using all the properties that we said. This equation is equivalent to the following equation. The derivative with respect to z of this alien derivative minus a, the alien derivative acting on phi, plus 2 z to the minus 2 phi, the alien derivative. In here, I use the distribution property. This is actually a derivative, so it just satisfies Jacobi. And the alien derivative of 1 over z is vanishing, because 1 over z sure is a formal power series, but it's actually more than that. It's an entire function. Perfect. So you see in here that by applying the alien derivative to our equation, we found that the alien derivative at Ka satisfies this homogeneous equation, linear and homogeneous equation. However, we can construct yet another object that satisfies exactly the same homogeneous equation. So this is the first thing that we studied. The second thing that you can do, obviously, the derivative with respect to z and with respect to this trans-series parameter, they commute. Hence, I can take the derivative with respect to sigma of the same Riccati equation. And I'm going to get that the derivative with respect to sigma of the trans-series solves the same linear and homogeneous equation. It solves exactly this equation in here. But since this is a linear problem, first order linear problem, it means that these two guys must be proportional to one another. The alien derivative acting on our trans-series answers must also be equal to some constant, which might depend on the point, it might depend at which point I'm working on A, on the trans-series parameter, but it does not depend on zeta, times this sigma, the same guy. So you see why it's called the bridge equation. We have moved from the alien world to the standard calculus. So let me be a little bit more specific now, because we gave a particular parameterization. This is something popping out. Okay, I can look at that later. Okay, let us have a look on the left-hand side. Because remember, we wanted to compute the alien derivative acting on this transseries. And for some reason, I changed name and I call it S0. Let me, well, I really don't want to change name at this stage. So let me try not to introduce any error. So what did I put? E to the 8z. That's good. 8z, 5 to the z. So this alien derivative is going to give me sigma to the n, e to the k plus k8z plus 8z, the alien derivative without the dot acting on this guy. And so in here, I forgot an n. There should be an n sitting in here. Good. So this is e to the k plus n, 8z. Right-hand side, well, it's very similar. We just need to take a bunch of derivatives. And sigma to the n minus 1, e to the n, a, z, phi to the of n. And at this point, we want to match both sides. So this must be equal to that. So the first thing that you can do, you can see that in here, only positive powers of sigmas are appearing. So this object must also contain only positive powers. So we can write it as an infinite series of some coefficients, sigma to the n. Furthermore, the other thing that you can check is that not only it must contain the same powers, but the exponentially suppressed corrections must be of the same type. The left-hand side has the combination sigma to the n, e to the k plus n, 8z. So the right-hand side must match both the powers of sigma and the exponential factor. So if you do this little calculation, you will see that the only possible solution is for ak of sigma to be ak sigma to the 1 minus k. And this leads to an infinite set for the alien derivatives. We get that the alien derivative like phi n must be equal to 0. And I think at this point I need to flip sign because yeah, so let me, good. So let me define A to be minus S0, just because in general, well, I always have in the back of my mind exponentially suppressed corrections, while the way in which I started, I call them e to the 8z, so they were not necessarily exponentially suppressed. Of course, I didn't tell you what A is. Where did I put them? Yeah, here we go. So let me just change A to be minus S0. And at this point, the equations become delta k S0 equal to 0 for k bigger than 1, and delta k S0 of phi n is equal to ak n plus k phi t of n plus k for k smaller or equal than 1. So we get this infinite set of equations for the alien derivatives. And remember, let me write it again, note, just because the alien derivative at a point is not vanishing, is vanishing, for k bigger than 1, this you cannot infer that k S naught is a regular point. We saw yesterday an example precisely that was going against this. So for example, delta 2 S naught applied to the perturbative expansion. So I go back in here and I saw that this should be vanishing. However, this is not the only possible way to reach the point 2S naught and read the singular behavior. If you compute delta S naught of delta S naught of phi 0 and use the second equation, you will see that this object is 2A1 squared phi 2 tilde. So you see that this is telling you that 2S naught is not a regular point for phi 0 tilde. At this point, with this infinite set of alien derivatives, we are in the position to compute the Stokes automorphism. And for simplicity, let us compute the one in the positive direction. You can do that. The one in the negative direction is a little bit more painful. Okay, so just to remind you, this was summing over all the singular point and take the alien derivative at that singular point. But we know already that this object is 0 for all k bigger than 1, is the first equation in here. So this simplifies dramatically the Stokes automorphism in the positive direction. The negative direction, you can still do it, but there is more combinatorics and the action is different. So what is this object? We can expand the exponential. 1 plus exponential of minus S naught Z, delta S naught plus a half e to the minus 2S naught Z, delta S naught squared plus dot dot dot. So we have just one type of alien derivative appearing, just that the alien derivative at S naught composed multiple times. And we also know what the action of this alien derivative does on the nth sector. It's this constant A1, n plus 1, by n plus 1 tilde. So, okay. So if you act with this guy multiple times, little combinatorics, you get A1 to the K and then some O'Connor symbol. Okay, so we have the first bit of the equation. We have computed all the alien derivatives in this particular direction. There was actually just one repeated over and over and over. What is the Stokes automorphism doing then? Well, we have just written it as the exponential series. And so if you just put this one in and you just do some rearrangement, you get the following expression. Choose k out of n plus k, e to the minus s naught k z times by n plus k tilde. So you see that this is telling you that if you compute the difference in resummation, let's say, between the two sides of the singular direction 0 of the nth instanton sector, you can write it as an infinite sum in which higher instanton sectors are popping out. All of them are exponentially suppressed. Had we computed the Stokes discontinuity in the pi direction, we would have found all the remaining instanton terms, so the one where we were actually looking at them backwards. So the second instanton sector would have seen the one instanton sector and the perturbative expansion in the pi direction. But as I said, the pi direction is a little bit trickier to study. So let me just do it in here because we're going to get a very nice equation at the end. So this is on each single building blocks. Let us put it together on the full trans series. So we want to take the Borel summation of the full trans series. And we know that this is in the negative direction composed with the Stokes automorphism. So we have just computed the Stokes automorphism. So first of all, let me write it by spelling out everything. And at this point, I can use this equation in here. So we get S naught minus the sum for n equal to 0, infinity, sum k equal to 0, infinity, sigma to the n, e to the minus n, S naught z. And then let me plug in this expression. A1 to the k, choose k out of n plus k, e to the minus S naught kz, and phi tilde n plus k. So you see now that we want to label stuff according to their exponentially suppression weight. And this guy combines with this guy and gives me e to the minus n plus k S naught z. And together with this one, it couples up pretty nicely. It gives me exactly the correct n plus k exponential suppression term with its associated perturbative expansion. The rest, it's very simple to see that you have sigma to the n, a1 to the k, and some combinatorial. That is nothing but a binomial expansion. So let me define capital N to be little n plus little k. I can rewrite this expression as S naught minus of the sum of capital N, e to the minus n S naught z, phi tilde n. There were these two terms. And whatever is remaining is this finite sum, is the sum for which one did I keep? K, 0, all the way to n, a1 to the k, sigma to the capital N minus k, and the binomial. But you spot immediately that this is precisely the expansion of sigma plus a1 to the n. So you see that the only thing that the Stokes automorphism has done is to spit back the same trans series where you simply shifted the trans series parameter by this constant a1. This is our connection formula in this particular direction. Equivalently, there is a quicker way, well, if you wish to do it, we can just do it from the bridge equation. So from the bridge equation, rewritten this as not variable, we have this object. The alien derivative is just given by this expression in here. And so if you want, the Stokes automorphism in the 0 direction is the exponential of delta S naught, which is nothing but the exponential of a1 sigma to the 0 d sigma. But this is nothing but the shift operator. I don't know why I wrote the sigma to the 0. It's just 1. This is just shifting the value of the trans series parameter, which is exactly what we found in here. So in this case, the Stokes automorphism in this direction is very simple. The thing it does is just shift the trans series parameter by this constant a1. And it's crucial, so let me write here, crucial our perturbative expansion knew about all the non-perturbative terms. Well, you can say this about any sector. Any sector, phi n, will know about all the other sectors. However, since in this case I just focus on the positive direction, it's easier to just focus on phi 0. So just to see a bit more concretely what this does for us, let us go to a simpler case. The case of a two-term transeries. So it's a transeries in which I have just two parameters, phi 0 plus sigma 1. And let me say that the action is e to the minus s naught z phi 1 tilde. So of course, this is not going to be a generic solution to a nonlinear problem, but I want to redo the same analysis to see some concrete results. So we can assume that these two guys are once again in the same algebra. And now the algebra is very simple. Sorry, the Riemann surface is very simple. It's just a universal covering of C minus the 2 point S naught and minus S naught. So if you repeat a very similar analysis in this case, you can see that the alien derivative of one is captured by the other in the positive direction, let's say, and the alien derivative of the second is vanishing. And the same goes on in the opposite direction. The alien derivative of phi naught is 0, and the alien derivative of phi 1 is a minus 1, phi 1 tilde. Sorry, not phi 1, it's phi 0. Good. So I would suggest for the students to repeat the analysis of the Stokes automorphism in this case. It's very simple, both in the positive and in the pi direction. And you will see that it's fairly similar to what we did before, just a little bit simpler. But we're going to be using this particular example in a second to derive the large orders relations. So suppose from this example that we only had access to our perturbative coefficients, phi 0 tilde. Then we can define a resum perturbative expansion. So let me call it perturbative. And let me take it to be, for concreteness, I could have taken any direction, but let me just do it like this for simplicity. Exponential of I theta, e to the minus tz, the Borel transform of phi 0 tilde of t, where I'm correlating theta with minus the argument of z. It's not necessary, it's just to put the branches in some nice position. So I pick zeta to be, well, we think it to be our real and positive coupling constant. So I want to integrate along this direction, but I cannot really do that. I need to go slightly above or slightly below. But if the argument of zeta is slightly positive, then I'm going to be picking that particular direction. And at this point, we play some little complex analysis problem. We want to write this function using Cauchy theorem. So we write it as 1 over 2 pi I, the contour integral of this function, w minus z. So this is the z plane. Sorry, this is the w plane, since I'm integrating in the w. This is the point theta, and this is my contour of integration. However, we know already that this function will have some branch cut along the positive direction. Because if I take phi perturbative of z plus I epsilon, z bigger than 0, minus perturbative z minus I epsilon, this is directly related. So in here I'm anti-correlating. So you see if I go slightly above, then it's actually the integral is slightly below. So this is s minus minus s plus. So we know that there is going to be a branch cut in this direction. And in general, there's going to be branch cuts all over the complex plane and all the other Stokes directions. This is why I restricted myself to this simple case in which we only have for phi naught a branch cut in the positive direction. In general, you will have a lot of branch cuts. And the argument that I'm going, you have to generalize it, but the key idea stands. What we're going to do, we're going to close the contour of integration the other way around. Modulo convergence of the integral at infinity, we can rewrite this Cauchy integral in the following way. We can write it as 1 over 2 pi I, the integral between naught and infinity of the discontinuity in the 0 direction of this perturbative object divided by w minus z. Again, in general, you're going to get a sum of discontinuities and so on. But for the present case, where I just put a single direction of singularity, is easier. At this point, we expand this object in the usual way. Wn z to the minus n minus 1. So if we plug it in the above expression and we commute the sum with the integrals, which of course we cannot do it, but we're going to do anyway, and we'll get an asymptotic 2. Minus 1 over 2 pi I, sum 0 infinity, z to the minus n minus 1, the integral between 0 and infinity, the discontinuity along the 0 direction of w to the n in dw. And you see that we have found an asymptotic expansion in large Z, but we know already that the asymptotic expansion, we've discussed it over and over, that these asymptotic expansion coefficients are unique, which means that whatever is multiplying Z to the minus n minus 1 must be our original perturbative coefficients. Perfect. And at this point, we use the discontinuity of this perturbative expansion, obtain via the Stokes automorphism from before. You can write this one as the identity minus the Stokes automorphism in the 0 direction by 0 tilde. Which for the easy example of the two terms transeries, this takes the forms minus a1 e to the minus s naught z by 1 tilde z. In the case of the one parameter transeries, you're going to get an infinite number of terms. And they're all extremely interesting, but just the key features will be enough just to focus on this one term here. So at this point, we can plug this in the above expression, or actually in the coefficients directly. And we get these large order relations. Sum of k bigger or equal than 0, the integral between 0 and infinity, e to the minus s naught w, w to the n, ck1 w to the minus k in d w, where I wrote our one instanton sector in terms of some new coefficients, the instanton perturbative coefficients, the ck with subscript 1. If I wanted to be consistent, I could have put a 0 in here to denote that the C and 0 are the perturbative coefficient. Again, in the case of the one parameter transseries that I did before, here I would have also got e to the minus 2 s naught z phi 2 tilde, and so on. All of these would have contributed, each one of them with an exponential suppressed correction, and each one of them with their own perturbative expansion. At this stage, it's easy to do this integral, and we get the following relation that we have seen many times in this whole school. C01 plus C11 S naught divided by n plus C21 S naught squared divided by n minus 1 plus dot dot dot. So you get this natural expansion in terms of, well, the factorial growth. The instant on action is below, that's the numerator. This A1 that I should have given the name before, so this A1, in this case it's called the Stokes constant, or in general, these are called the holomorphic invariant of the problem, which are very difficult to study. We have seen various interesting methods. In few cases, Chris gave us some beautiful ways of computing them numerically, in the case when they're integers. And that was the case because he was studying the steepest descent contours, so they were really related to intersection numbers. But in general, these constants are not necessarily integers if you're not coming from that, that angle. So they're very difficult to compute. S naught, which takes the exponential suppression, is the, well, instant on action. I keep on saying instant on because I'm coming from high energy, so, but they are whatever non-perturbative effect are behind your exponential suppression correction. And you see here that these guys in here are nothing but the perturbative coefficients in the instanton sector. So in general, given the precise form for the Stokes automorphism, you're gonna get, well, this is just one of the terms. As I said before, if I had, from the Stokes automorphism, I had this second term, it's very simple to see the action of that term. So we're gonna have A1 e to the minus 2 S naught Z times the 2 instanton sector. What is gonna give you? It's going to tell you that the perturbative coefficients have the one instanton part, the one that I just wrote. So let me just write two terms. But also, it's going to have the 2 instanton part, which is exponentially suppressed compared to the 1 instanton. You see that there is an 2s naught at the numerator. And this is multiplying the perturbative coefficients in the 2 instanton sector. And so on. So Gerald already mentioned various numerical ways of actually reading all of these coefficients. So one of the things, of course, that you can play with when you generated enough perturbative coefficients, you can take ratios, you can try to understand what the factorial growth is, and you can try to fit for the Stokes constant and the instanton actions. But then you see that the second instanton sector is exponentially suppressed. So first you need to get rid or deal with this whole series. But remember, this C01, C11, and so on, they were all part of the 1 instanton expansion. So we know that these guys are factorially growing. So what you can do, you can think of this expansion in here as, once again, a formal power series, a factorially diverging power series, where the coupling constant now is 1 over n. You can resum it using Borel-Padé or conformal Borel-Padé. So what you can actually do, you can resum all of these things, all of these blocks in here, for large n. for different values of n. And you subtract it from your coefficient C naught, Cn naught. This will give you access to the two instanton sectors, provided you computed, well, A, enough perturbative coefficients, and B, with enough numerical precisions. And then you can repeat the story. From the subtracted perturbative coefficients, you can read the suppressed terms. You can find this perturbative expansion using Richardson extrapolation, for example, and then you can subtract the full two instanton sectors to the perturbative ones. And you can go and read the three instanton sector and so on. Good. So since well, 10 minutes, let me just go towards my conclusion. Perfect. Because I've seen there's a few questions in the chat. So first thing we have seen is this Fourier summation for Gevrey-1 series, which of course are not generic by any means, but they cover, well, we have seen in this school a lot of beautiful examples, physical applications, mathematical applications, where these Gevrey-1 series are popping out. The singularity structure is captured by this alien derivative. Putting all these alien derivatives together will tell us about the monodromy properties, because at this stage I was just focusing on one particular direction. But then you can play the game of you keep on moving the direction. You're going to encounter multiple Stokes directions, and then eventually you can go back to yourself. The trans series in general will go back to a mess of itself. So in general, you should not expect any particular beautiful monodromies. However, for example, for linear problems that we have seen exponential integral, incomplete gamma functions, then you actually get some beautiful monodromies behind. So yeah, as I was saying, in general, we have multi-ramified analytic functions on some very complicated Riemann surface. Of course, for a generic physical problem, you're not going to have random singularities. They're in many cases going to form a lattice, or they're going to be a special locations which have to do with the size of the non-perturbative effect. However, this is something that, of course, just the study of the resurgent properties is not going to tell you. So, of course, when I say the physical origin of these exponentially suppressed corrections, is something that you have to work out for yourself. For example, in Gaussian-Stokes, we have these beautiful examples of these complex instantons. Resurgence tells you, look, there are some exponentially suppressed corrections in here, and then you need to go back. And in general, from a path integral point of view, an Euclidean path integral point of view, you should expect to receive contribution from all the classical configuration, the classical solution to your equation of motion, which are living in a complexification of field space. For path integrals, of course, this is very difficult to do. We had Sergei Stoke on the first week of term, where he was mentioning some of the problems of the tymbals in infinite dimensions. But this is the idea whenever you have some sort of path integral interpretation. Chris gave us some beautiful examples, path integral oriented, where you were precisely seeing that the Stokes jumps were accompanied by jumps in topology of the tymbals, and everything, all the origin, the physical origin of the exponentially suppressed correction was clear from these beautiful plots. In general, however, just because you have a singularity at a certain point, you don't know the origin, is something that you have to study from your problem. And finally, well, as a very useful tool to understand this, the alien derivative in the Stokes automorphism, you can play with this large order behavior. They are extremely useful if you don't have access. Say, for example, that you can compute as many terms as you want in the perturbative expansion, but you don't know them as an analytic function in M, or said differently, you don't know how to resum, how to do the Borel sum. Well, this large orders relation that I sketched in here in the simple example of a two-term transitis will tell you more about the Stokes jumps. So in this case, I gave you the one parameter transitis where all the jumps were controlled by a single variable, this A1. This is something that for generic problems, you should not expect. You should expect an infinite parameter transitis. So you should expect that at various instants of order, you're going to have different Stokes jumps appearing. However, these large order relations are extremely useful to decode all of this information. Good. So let me finish in here and let me answer some of the questions.
Okay, so let's thank Daniele for a very, very nice and clear account of Ecalle Resurgence.
Thank you so much. I saw immediately the
really,
last comment.
Really. So I have a couple of very quick comments. I mean, this is something that you mentioned, but it's worth emphasizing that this Ecalle Resurgence and what you showed here really holds in very general classes of problems, systems of nonlinear ODs, even classes of PDs, and so on and so forth.
Absolutely.
It's a bit of a curious thing, but even the fact that you have simple sort of singularities holds generically. Instead of a log, you would have a branched power, t minus t not to the power alpha. Otherwise, it's basically the same generically. The other thing, so you may have mentioned, but if you did, then I'm sorry, towards emphasizing that you don't need everyone. So one sort of uses a Eccalle's critical time and all these classes of problems. So it's a change of variable, nothing more. And
I did not mention this, but Gerald did. Thank you, Ovidio. It's definitely worth emphasizing. Yeah.
Okay, and the last thing, which is also minor of sorts, is that the Stokes constants can also be calculated in closed-forming integrable models.
Yes, definitely. Yeah, absolutely. Thank you.
So yeah, and with that, sorry to take time. Let's see. Do we have questions?
So I think it's Mark's comment on the fact that the two instanton part comes with a factor A1 squared. Thank you so much for spotting that. So I corrected it as soon as I saw it. I don't see anything else. I cannot see if there are raised hands though.
There is one raised hand.
There is a raised hand. There is. Yeah, let me see here quickly. Okay, let's see, where is that? Okay. Yeah, okay.
Hello. Yes.
Hello.
Yes, I can. Do you hear me? Yes.
Yep.
Yeah, sure.
I was just wanting to make a remark about the fact that what Daniele has well presented is just one part of Resurgence Ecalle studied, because what he spoke about was Ecalle called equational resurgence, and there are different ways that resurgence can appear, which he called equational resurgence, which is more akin to what Chapman and Train spoke about, where the parameter for which we want to do resummation is a factor in the equation, and not one of the parameters in the differential equation. And so it's quite interesting, but I think that many aspects of resurgence, as nevertheless not been created in this conference. What has been said is quite interesting, but we should recall that in the work of Ecalle there are much more things not really not easily accessible, but nevertheless a good deal of work can be done around this.
Thank you. Absolutely. Well, unfortunately, I only had 3 hours. So, and I have to say, of course, I gave my biased view coming from higher energy physics, but you're absolutely right.
Yeah, I just wanted to people not have the impression that the basics of everything has been done. The basics of some aspects of resurgence, but the domain is large.
I should also say this program is just at the very beginning, right? So Dinesh has been working super hard. So there's going to be focus weeks. I'm not sure about like what, but I'm sure there's going to be some focus weeks more on this mathematical aspect that you were pointing out. Thank you. Oh, Gerald, can you comment on the appearance of log terms in the large order behavior in this language? Log of n or log of h bar, as Gosha was mentioning before. So for log of n, it's simple. I don't know. I have not encountered them. But for the log of h bar, I would expect to get just some polygammas out, roughly because you can generate, if I take the derivative with respect to s, this is going to be whatever. Then I set it s equal to n, right? So this is going to give me something of this type. And of course, like the index of this one is directly correlated to the index of the gamma. And so this is going to give you some polygamma instead of factorial. But I think you were probably asking more about the log of n, Gerald. It's very, I have to say, I don't quite like that we cannot really talk simultaneously. Yes, both they are related. I see. Good. I guess you're saying that in here. No, sure, yeah. I have to say I've not encountered that in any practical problem. Yeah.
Is there another? Let's see. Yeah, there is. Sorry. Okay. Here is another question.
Yeah.
Hello, David. David, are you there?
Did someone speak to me?
Yeah.
No.
Yeah, I thought there was a raised hand from you.
No, I'm sorry. I must have pressed some button by mistake.
Okay.
I'm listening in all, and I have nothing to say. Thank you.
All right, that's good. Okay. Yeah. Well, let me come up with a quick other comment, because you mentioned this endless continuability. There's not automatic, actually. They're very, very simple, extremely simple linear difference equations with non-constant coefficients, basically like the factorial, where you get natural boundaries. However,
I see.
There is a way to go through the boundaries. I mean, one way is a Ecalle cohesive continuation. I mean, they're spectacularly simple. And there is something that replaces this endless continuation by a very, very clever technique that Ecalle came. We can discuss at some point.
I would be extremely happy to see some of these examples. Like, of course, you encounter such examples whenever you're dealing with some Q series expansion, but of course over there you're working in a different domain, right? You want to work on a disk, so it's fine. I would be extremely interested to see these examples.
I'll send you a paper of mine in which I go in a different way, more analytical.
Thank you.
Yeah.
Good.
Is there anything else? Let's see. No? Well, then let's again thank all speakers. I mean, it's a lot of effort, and the result was a series of very nice and clear talks. And with that, I think we'll go to the next stage where you have the coffee type of meeting. Unfortunately, I cannot be here for the coffee meeting.